right, I think we are ready for the second talk of the day. So for our second talk, we have Hanna Kim from the University of Illinois at Urbana-Champaign, who will talk to us about maximization of the second Laplacian eigenvalue on the sphere. Hanna, the floor is yours.
Yeah, hi, my name is Hanna Kim. I'm a third year PhD student in UIC. Yeah, I want to thank first the organizers for organizing this mini conference. Today I'll be talking about maximization of the second Laplacian eigenvalue on the sphere. And today the plan is first I'm going to give the introduction to the problem, and then I am going to prove the results by constructing trial function. And lastly, I'll briefly talk about related work and maybe future direction on this problem. So this was a summer project advised my advisor, Professor Rick Laugesen. So let's talk about the setup of this problem. So consider Laplacian on the sphere Sm, and then we'll have the sequence of eigenvalues going from 0 and increasing to infinity. And I'm especially interested in the second eigenvalue. And the goal is which remaining metric, which is G. So this eigenvalues will depend on this metric. So which Riemannian metric maximizes area normalized lambda 2, the second eigenvalue. So let's talk about the known results. So first eigenvalue was is maximized under the standard metric, which was proved by Hirsch in 2 dimensions, and Al-Sufi and Elias in all dimensions. So the eigenvalue is maximized under standard metric. So the sigma is what I use for the area of the sphere. And for the second eigenvalue, Nadarashvili, in 2 dimensions and Petridis in even dimensions, they show that the second eigenvalue for S2 is bounded with 16 pi. And notice that this is sharp, and for the second eigenvalue, it's not. And so this means that there exists a sequence of metrics going to that of 2 disjoint spheres with the same area. And I'm going to give the analogous generalized version of this upper bound in all of the dimensions. So here is my main result. If G is a Riemannian metric conformally equivalent to the standard metric on the sphere, yeah, of course, in S2, it just needs to be Riemannian metric because there's only one conformal class. Then our area normalized eigenvalue is bounded with this m times 2 sigma m to the 2 over m, where sigma m is the volume of the standard unit sphere. And as you can see here as well, it's not sharp, but when m equals 2, we get the same result as Nadarashvili. And I just wanted to point out this is what I call for as my Riemannian metric. I'm going to call it as G. And then we have this dimension adjusted to our area terms on the left-hand side and the right-hand side as well. Okay. And I'm going to talk about this will be more clear as I show the proof. The implications are as same as before. The upper bound will be will imply that we would have to have a sequence of metrics that is going to 2 disjoint spheres. And this is confirming the conjecture by Gerard Nadarashvili and Proterovich is 2009. So we're going to build trial functions satisfying this Rowley quotient, and this is more simplified approach to show the upper bound because we are gonna use very direct trial functions. So we're gonna plug in our trial functions to this Rowley quotient, and this U will be the valid ones, and this dVg is gonna be my volume measure with respect to G. Okay, so we're gonna start with the basic spherical harmonics. So I'm gonna denote G naught as a standard metric on the sphere, and we would have first eigenfunctions on the sphere with respect to standard metric, Laplacian with respect to standard metric, and I'm gonna call this YJs, which are spherical harmonics, and it, of course, its eigenvalue is m with multiplicity n plus 1. Okay, and so using them, we're gonna have trial functions, n plus 1 number of trial functions. Okay, so before we move on to the proof, I would just like to give some maps and concepts needed for the construction. So first, Mobius transformation on the whole closed bowl. I mean, of course, we're just gonna use it on the sphere. I'm not gonna give like the detailed formula is not really important, but they kind of work like translations on the sphere. So what you would get is, with respect to this x, if I fix a point x, then you can just think of it as like spheres, all of the spheres moving towards this x. Okay, and this will be like translation on Euclidean space. And spherical caps, and which are just like half space on Euclidean space. And I'm like starting from, so the way I build this spherical caps are related to the last steps of the proof. So I'm just going to give like a little bit of explanation about that. So I start with hemisphere, and then I move the hemisphere around with this Mobius transformation. And this Mobius transformation is with respect to this T. And P is a point on sphere, and T is from 0 to T. So the spherical caps would look like, so I will be only talking about the big caps, meaning that this would be my H. Yeah, and then I can just move it around using Mobius transformation. And one thing that I I want to point out about this HP, T is that, so we on the sphere only, we have this nice little formula, and as you can see, so we're not including T equals 1 because, well, the Mobius transformation is not continuously defined to when T equals 1. But as T equals to 1, as you can notice from the spherical cap, the upper bound will be just 1. So that means that the spherical cap will it will cover all the sphere, almost all sphere. But of course, when T goes to 0, it will just collapse to a point. Okay, and then that was slow. Reflection map. So reflection map is just reflection map. And the way we build it is the same. I define it on the hemisphere, and then I move it with Mobius transformation. And lastly, using this reflection map, I'm going to define the fold map. So on one spherical cap, if I have, for example, this might be too small. So if I have a spherical cap that's, let's talk about the big caps. And what this fold map does is that it's just folding one of the spherical caps to another. Okay. Yeah, so we have the translation and this fold, and we're going to build our trial functions using these tools. Okay, So we have this. So here the orange one is our. So each component of this ones are trial functions, and to show that this is a valid trial function indeed, we have to show two things. First, it's orthogonal to the constant, and secondly, it's also orthogonal to the first excited state. And we claim the following vector field gives n+1 number of trial functions. So first, we compose with fold, and then we compose with a Mobius transformation, and these are just components are just the spherical harmonics, so it's needed at the last step. So what it does geometrically is that, so by folding first, by finding a right spherical cap, we are going to make it orthogonal to the first excited state. So which kind of makes sense when you think about the spherical harmonics. So what folding does is we're reflecting, we're doing even reflections on the sphere. And after finding the right spherical cap, let's say this is H, and then we have its center of mass at here. And then we are going to move the spherical cap on into this towards this center of mass, so that we would have the orthogonality to the constant. And we're gonna first prove the orthogonality to the constant part. So we adapt the classical method by Hirsch and show the following fact, which is saying that the vector field is orthogonal to the constant. And this is possible by applying corollary phi from Laplacian, paper by Laplacian, and it's go into too much detail because I need to check like a bunch of conditions, but it was saying that if you satisfy a certain conditions and you have this domain on the sphere, and it satisfies a certain conditions, that means that you can just apply the center of mass. And it works with the push forward measure with fold map with the original volume measure. Okay. And now we're going to prove the first, oh, sorry, just skip that. And we're going to prove the orthogonality to the first excited state. So basically what we want is that we want our vector field to be orthogonal to our first excited state, which we are going to call it as F. And we want it to vanish at some point, P comma T, where P is a point on the sphere and T is some point on 0, 1. And we're going to use this degree theory by Patrides in 2014. And what it says is that suppose we have a continuous map that's going from sphere to sphere. And if it satisfies this reflection symmetry, so you can kind of see that if you map a antipodal point, and it's the same thing as if you map the original point and then reflect it on the sphere, then the degree of this map being non-zero, that means that it's not homotopic to a constant map. In particular, if m is odd and then degree of phi, the map is 1, and if m is even, then the degree of phi is odd. This part, in particular part, is not really important in our discussion, but yeah, so it's related to this degree theory. So, and this is called, we're going to call it as reflection symmetry, reflection property. And so how we are going to prove orthogonality to the first excited state, our strategy here is use contradiction. This part proceeds similarly with Freitas and Laplacian if anyone's interested. So basically, we want to prove the vanishing of the vector field in order to prove the orthogonality to the first excited state. And oh yeah, I just rushed to the end, and I'm just gonna give like basic plan of how we're gonna do that, and I'm gonna explain the details later. So when t is equal to 1, it's the vector field. So notice that I divided with its norm so that it's going to the sphere. So it's a map from sphere to sphere, and then I'm going to prove that it's actually constant. And I just wanted to remind you that I have not defined it when t equals 1, and it's continuous, so I'm going to explain that later. And when t equals 0, I am going to prove that it satisfies the reflection symmetric condition, and by the fact that topological degree is a homotopy invariant for continuous map between spheres. So that means that we have a contradiction. So that means that the vector field has to vanish at some point. Okay, so we're going to prove the reflection symmetry when t equals 0. So I'm not going to go into too much details because it's all calculations. But so let's think about how the vector field looks like. So it's an integral composed of the Mobius transformation, the fold map, and then I was moving the sphere, translating the sphere with respect to this center mass here, C. And if I prove that when t equals 0, that all of these maps has reflection symmetry, then I would get the reflection symmetry. So here, if I verify it with respect to Mobius transformation and fold map, and it also has center of mass has reflection invariance, then naturally we would get the reflection symmetry when t equals 0. That means that the vector field itself has reflection symmetry. Okay, so and then as I said, the Mobius transformation and fold map they're not really defined continuously as t goes to 1, but we can actually understand the vector field in the limiting case as t goes to 1 and actually define continuously. So we're going to show that. Since the fold map, as I showed it for the spherical cap, since the fold map goes to almost identity map, except at the single point Q. So what I mean is that, so let's think about the points, the limits going to, as P goes to Q. So if we have a sphere and I have a spherical cap like that, and yeah, I had like P here, and what I had was, let's say it's going to limit that looks like that. So P is moving to, for example, Q here. And what's going to happen is that as T goes to 1, so that means that the spherical cap will cover almost all sphere. And as T goes to 1, of course. And except at a single point, which is P, which is Q, right? Which is the limit of this point P. This will just, because this fold map will keep folding as T goes to 1. So that means that it's gonna go to its antipodal point, which is minus Q. So as P goes to Q and T goes to 1, the vector field itself will go to a constant, which is, and it will just depend on the metric. So, and also the center of mass, because it covers all the sphere, it's just gonna be the center of mass for the whole sphere. So then using that, we would have the contradiction. Okay, so since we proved that these n+1 functions are indeed valid functions, we can put it in Rowley quotient by plugging them in trial functions to the Rowley quotient. We would have this inequality. Okay. And what I'm going to do is that I'm going to move it to left-hand side and then sum it up for j equals 1 to n plus 1. And for the left-hand side, these points, we know that however I move that, these are just points on the sphere, right? So if I move the sum inside, so that means that it's going to be 1. So the resulting integral will be just the surface area of the sphere with respect to the certain metric g. Okay, and then we need to take care of the right-hand side. So after taking the sum, I move the sum inside. A fun story of the original version that I was writing with my advisor, the paper. I actually changed the order, and Professor Karpushkin, and I asked him for feedback. He kind of suggested, yeah, how about changing the order? And then it actually gave much better result. And it turned out it was actually what they did in the Anyao paper. Anyway, that's what happened. So yeah, and Professor Karpushkin was gave really helpful feedback. So yeah, after putting the sum into the integral, and then we have to use Haldor's inequality to use conformal invariance. So this would be our 1 over p, and this will be 1 over q. And to simplify the notation, I'm just gonna use this notation for the gradient, the norm of the gradient for vector value maps. And I can just write it like that. Oh yeah, sorry. And then we have to move this to left-hand side. Then we would be getting area term to the 2 over m, right? And then we would just have this term. And by conformal invariance, we would change it to standard metric. So everything's the same. I just change it to standard metric G naught. And I expand the fold map into 2 parts, on the spherical cap and on the reflected side of the spherical cap, right? And by conformal invariance, again, because reflection is isometric, we can just cancel them out. And then I would have the same 2 terms, right? So I'm going to take the 2 out. And so we would have 2 to the 2 over m. And we would just have, sorry, this Mobius transformation inside. And by using conformal invariance again, I can just change conformal invariance again. We would just have the last term. So remember that I dropped the spherical harmonics, the coordinate functions. So now we have to calculate this coordinate functions, the integral, right? The gradient integral. And luckily I can just project. So first, this term will be smaller, strictly smaller than the sphere itself. And then I can just calculate this gradient by projecting from the Euclidean space to sphere. And with respect to standard unit vectors, of course, these EJs are standard unit vectors. And I'm putting back the notations, the sums back in. And so we can now actually just calculate it, right? So after expanding it, we would have just 1 minus EJ dot I square. Maybe there should be parentheses here. So, and then, so this, we have n plus 1 number of ones, and then I can, so this is again just coordinate functions on the sphere. So this would amount to 1. So we would have m. So by taking the constant out, we would have that nice term. And then I just need to plug this back in to here. So that would be our result. So yeah, so although it's not sharp, you can kind of see that how we can get close to the upper bound, right? By moving the spherical caps around, and then it would have to be like it would have to look like something like two disjoint spheres. Okay. Yeah, this was all my proof. And I just wanted to introduce like some of the related work. Using this trial function method, like folding and Lewis transformation, there were some interesting results about their Neumann eigenvalues on hyperbolic and Euclidean space by Freitas and Laplacian, and then third eigenvalue of Rowley boundary problem by Gerard and Laplacian in 2019. And there was not using this method, but using there are other, if they're using very interesting methods. There were some maximization problem about first two Steklov eigenvalues, maximization results, and then for the higher eigenvalues for S2, for Nadrashvili and Sire, they proved this for lambda 3, and Karpushkin and Nadrashvili and Panskoy and Poltravich, they proved it all case is NK. And so, yeah, I just wanted to talk briefly about the future direction. So we can also think of this problems on real projective space. So we do have like this results on RP2. And for tori, we also do have some results on T in two-dimensional case in some numerical works. And we can also think about, I guess, higher eigenvalues for the higher dimensional sphere. Okay. Yeah, thank you. Yeah, thank you so much for listening.
Thank you.
Oh yes. Oh yeah. Sorry. I just wanted to say one thing. So after Professor Karpushkin gave me the feedback, I realized this was in contradiction with the result by Professor Drouet. And my advisor and I were kind of surprised, and we asked a lot of help, and thankfully a lot of mathematicians gave really helpful feedback. And yeah, I also talked to Professor Drouet, and he was really nice. But I honestly couldn't figure out if there was an error in my paper or in his paper yet. So yeah, I'm not gonna say much because I don't want to speak for himself. But yeah, he was really helpful with the feedback. Yeah, and I just wanted to say that because yeah, there is a result like that. Yeah.
Thank you very much, Hanna, for this talk. It's really nice that you are very thankful for others people's work, but I think that your work is quite impressive in this paper as well. So you can think well of you for that. So does anyone have any questions for Hanna? So this folding method that you're using to maximize this second eigenvalue, do you think that, I mean, obviously if you try to extend this for higher eigenvalues, the computations become crazier and crazier, but do you think there would be a way to make the computations more abstract so that it would work for any number of for any index of the eigenvalue, or it really works well only in the bottom of the for say the first or the second eigenvalue?
Yeah, honestly, I didn't really like think deeply about it, but I just like thought about it. But I did think about it. But yeah, I mean, because if you think about the spherical harmonics, it kind of has like some symmetry into it.
Mm-hmm,
So I think it would definitely work if like you said, if we try to do like some more different approach of calculations, because yeah, and yeah, I definitely think so. And yeah, that's why I also included that maybe in future directions we can do it for the higher eigenvalues as well.
mm-hmm.
Thank you.
We have a question in chat from Chihan Tan, who's asking what's the intuition behind building these specific trial functions that you have used.
Oh, okay. Yeah. So basically, so if you look at the spherical harmonics, right, it has even modes and odd modes, right? So, for example, yeah, I don't remember the picture exactly, but so because yeah, we were doing a second eigenvalue. So let's say even modes look like that. It's not really exactly correct. So the first eigen, so orthogonality to the constant, it was studied. It has a long history, so we knew that it has to have some center of mass to make it orthogonal to the constant. And because considering this even mode, right? So we're gonna have to do like some kind of folding and do some even reflection to although with some it's gonna be some different metric, but with some folding on the sphere, right? Although it would not be the same as Euclidean space, it would result in like some orthogonality to the first eigenfunction. Yeah, so basically it started from the spherical harmonics. Thank you.
All right. Um, if it, okay, so Chihan Tan asks says thanks for the answer. So I guess it answers what they were asking. Do we have any other questions for Hannah? All right. If not, let's thank the speaker again.